All right, so thank you everyone for calling in today. Good to see you all and hear your voices. Our presenter today is OJ Tucker, who is going to be talking to us about a recent paper that he and colleagues published on the lifetime of a transient atmosphere produced by lunar volcanism. And so before I hand it over to OJ, I'll just remind everyone to please put yourself on mute unless you are speaking. Um, and OJ, would you prefer if we hold off on questions until the end, or would you prefer if people ask questions in between?
Folks can ask questions in between if,
All right,
yeah.
sounds good. In that case, I will hand it over to you, OJ. So whenever you're ready.
Okay. All right. Thanks a lot. So right, today I'd like to give really a sort of a broad overview of a recent paper submitted to, well, not submitted, but accepted by Icarus on the lifetime of a transient atmosphere produced by lunar volcanism. And sort of the sort of one of the broad motivations behind this paper was to think about atmospheric escape, um, relevant processes of atmospheric escape. Oh, I'm sorry, my computer fan is pretty wild. It should quiet down here in a minute. Um, but the paper is really a review of relevant processes of atmospheric escape applied to an early moon atmosphere. It's like an overview of those different processes for other communities that might not necessarily think about atmospheric escape so much. So like if you're focused more so on the geology and the volcanism, or if you're more so focused on the plasma interaction with the moon. So I wanted to give a broad overview of the atmospheric escape processes relevant for the moon, and then um, carry out some estimates based on those processes. And I'd like to acknowledge some co-authors on this work: Rosemary Keelan, Prabhu Saxena, both at Goddard as well, and Robert Johnson at the University of Virginia. Okay, I'll just do acknowledges up front. Yeah, so this presentation I actually gave at the National Society of Black Physicists meeting back in October. And so it's really a broad overview. So some of the things you might be familiar with, but I like to sort of promote that meeting. Lene Quick is really trying to promote Earth and planetary scientists at that annual meeting. And so if you come across it, I think is a good place to sort of present your work in planetary science, or if you have some sort of job opportunities, postdocs or or the like, you can either email me and I can pass them on to her, or you can email her. But yeah, I had discussions with Lene Quick. She's been thinking about the cooling rate for magmas over the lunar history and what type of outgassing you might get from that. And I'm sort of interested in that from how it populates the atmosphere. And also, Parati Prim had a lot of discussions with her. She's really thought in detail about transient atmospheres produced from like a comet impact, or even produced during a lunar mission, how long those atmospheres survive, and the transport of volatiles during that time. And so that's really, really relevant to this study here. More so, I'll be thinking about if you have an atmosphere on the moon. So this is really a follow-up to the Needham and Crean work. If you had an atmosphere on the moon that has like a Mars-like surface pressure, what's the relevant atmospheric escape processes for that? And the work has been supported by the LEADER survey node led by Rosemary Keelan. And so I think this is a really exciting topic because it just involves so many different areas of planetary science and allows for a lot of cross collaboration. And that's just one of the things that makes planetary science fun. But I like to highlight a lot of the recent interests on this topic here. You can see that there are two recent LPSC abstracts LPSC presentations that just occurred, thinking about how these volatiles could be transported to the PSRs over the lunar history. It's been studies thinking about the interaction between but thinking about the early moon's magnetosphere and also the interaction of Earth's magnetosphere with the lunar's early magnetosphere, and what does that mean as far as transport of volatiles to the poles? So these are some other, abstracts and papers that you might be interested in as well. Okay, so um, I'm sure many of you are familiar with these plots here, just showing that there's a strong evidence from various missions of, the moon's surface being hydrated. Right, we have observations from Cassini. You can see here sort of a global map showing an increase of hydration to the poles obtained from MQ, possibly H2O or OH, and also some of the frost in the polar craters shown here on the right. And so, right, the overarching question that we're all really interested in is, what's the, what's the source of this water? Is it constantly being replenished, or is it an ancient source? How has it evolved over time? How is it being lost? And so, right, how have volatiles evolved over time in the lunar environment? Um, that's sort of the broad background question of this study. So what's the source rate of water on the surface and in the PSRs? Folks have thought about the solar wind as being a replenishing source. If the solar wind is producing this hydroxyl and water on the surface, how is it transported to those polar regions? For the ancient source, where we're thinking about these volcanism, if we had this significant atmosphere, what would it take to transfer those volatiles to the PSRs over time? And what this study that we've done focuses on is what would be the lifetime of a significant early lunar atmosphere. So, right, because we're thinking about this early lunar atmosphere, right, it's really difficult because there are not many constraints. And so, and it's several different variables you have to think about. What's the source? What's the composition? You have to think about, you know, the external drivers like the solar flux, the solar plasma flux, was there or not a global magnetic field and all of these things. But some of the constraints that we do have, and this isn't an exhaustive list here, but some of the things that we can, sort of think about to constrain a problem is, right, we have the current state of the atmosphere. We know the current state is this collisionless, surface bound exosphere. So that sort of places a constraint on time, right? So if we had a significant atmosphere early on, we know that over time, eventually it has to be removed, by one way or another. Also, we have some estimates of the abundance of ice in PSR, so that can place limits sort of on an accumulation rate. And further, right, we can think about different processes, dynamical processes that destroy the ice over time. And so this can, these things can place limits on accumulation rate. Right, the abundance and composition of volatile gases. So we have volcanic samples, and they can really provide clues on what's the chemical state of the atmosphere. And that's important as far as absorption of solar UV. And if you have column of atmosphere significant enough such that plasma interactions would be important for either heating or also driving the escape of the atmosphere. Okay, so some backgrounds, as I mentioned before, this work was started off as really a follow-on study to the Needham and Kring work, where they estimated possible volatile gases produced by Mare volcanism over the history of the moon. And they show active periods are shown in red here as you see these different time increments on the graph. And, if you assume that these, volatile gases were equivalent to sort of an atmospheric mass, you can estimate sort of a surface pressure of the early lunar atmosphere. And so we follow on to that by taking those atmospheric masses and then thinking about the relevant escape processes. And so you can see a real active period was, between 3.9 and 3 billion years ago. And then the activity decreases as time goes on. And so here, based on an estimate of the volume based on Mare areas and depth, you can get a volume of volatiles materials. And if you have an estimate for the mass density of volatiles in that in these lunar samples, then you can get a mass of volatiles that potentially were released. And they did that for products like CO, sulfur, various hydrogen species, and water. And in the middle plot, you can see the estimated masses, and you can see a significant mass about 3.5 billion years ago, which similar mass to current day Mars, or 1.5 times current day Mars atmosphere. And based on that atmospheric mass, you can get a pressure. You can estimate a surface pressure. And another motivation behind this work was that in Needham and Kring, they adopted the atmospheric escape rates from an earlier work by Von Drake, who was thinking about, how long would it take to lose an artificial atmosphere produced on the moon from exploration. And so, in this work, we wanted to sort of update the atmospheric escape loss processes for more relevant cases for those early lunar atmospheres. So looking at specific mass species and the pressures that they estimated in the Needham and Kring paper. So this was the first estimate here. So Von Drake estimated that, after this graph here is showing the loss rate on the vertical axis and the total mass of the atmosphere on the horizontal axes. And so the total mass of the atmospheres in Needham and Kring are much larger than this 10 to the 9 shown here on this graph. But you can see they estimate that after you get past 10 to the 7 total mass, that the escape rate is assumed to be dominated by thermal escape, and that it occurs at a constant rate, which they estimate from like a surface genius calculation, which I'll talk about later. And this is for atomic oxygen atmosphere and for temperatures of about 800 Kelvin. And so these conditions are really different from what was suggested in Needham and Kring, right? The dominant species in that was CO, sulfur, right? So those masses are pretty different. And so we thought that this study would be useful, being that people who aren't so focused on atmospheric escape, sort of have adopted this earlier loss rate, which we can estimate a little bit better now. All right, so the presentation will go over some relevant atmospheric escape processes shown by this graph, by these animations shown here. Forgive, I should have the image credit here, but I don't have it. But this is sort of like thinking of Mars as an escape at Mars as an analog for this past lunar atmosphere. And you can have a thermal escape, where the escape is driven by the temperature of the upper atmosphere. And so some ways to estimate thermal escape are using Jeans escape. Also, if you have a fractional species, like we saw, we have fractional amounts of water and molecular hydrogen, the escape of those fractional species are limited by how they can diffuse through the major species. So in this case, how molecular hydrogen or water can diffuse through CO. And also a broad estimate, a really not broad, but an upper limit type of estimate on thermal escape that's frequently applied to early Earth, early Mars, or exoplanet type of atmospheres is this energy limited escape idea. And so I'll review those. And also I think thought about less frequently regarding these early moon atmospheres are sputtering of the atmosphere by the solar wind and also a photochemical escape of the atmosphere. These are non-thermal processes. So by non-thermal, I'm referring to processes that give atoms and molecules energies that are much greater than the thermal energy. So here we're showing, in this study, we took those atmospheric masses or surface pressures, the partial surface pressure for mainly CO and molecular hydrogen for each of the increments given in the Needham and Kring paper, each of the, I think about 500 million year increments. And we calculated loss rates for each of those hypothetical atmospheres. And this plot here is just showing, it's showing the log of the density, the surface density. So if you assume an ideal gas law, you can, and if you assume ideal gas law and you assume a temperature, we don't really know what the proper temperature is. This is something that really, needs to be constrained to understand what you start with. But if you assume a temperature right, you can get a surface density. And then from that surface density, with some approximations, we can estimate escape from the top of the atmosphere. So here we used, current lunar surface temperatures just for comparison. Now, that's probably not a good assumption, and it should be fixed in the, in the future, but that's what we did. Actually, we looked at a range of different temperatures, which we're going to talk about. Okay. So escape occurs in the region of the atmosphere where collisions are rare. So if you have a collisional atmosphere, you can't think about escape occurring from the surface. It really depends on the mass of the atmosphere, which determines where the exobase is. So below the exobase, typically it's assumed that the atmosphere is highly collisional. And above the exobase, collisions occur more and more frequently, but that's usually used as a hard cutoff level. And people often estimate thermal escape from that exobase altitude, or where possible precipitation can give atmospheric molecules enough energy to escape. So shown here, you can see this plot is just showing that, if we use look at those surface densities from Needham and Kring for CO, for a range of temperatures, for a range of temperatures similar to, the current lunar surface temperature, even all the way up to much higher temperatures of 550 K, these atmospheres are significantly collisional. So we really have to think about escape at the top of the atmosphere. And right, so just for background, the exobase altitude that I keep referring to is, again, it's temperature dependent, and is usually defined as the altitude where the average distance between molecular collisions are equal to the local scale height. So in an initial estimate, we sort of had some broad assumptions. We assumed a global atmosphere. We just used simple hydrostatic profile, hydrostatic law, isothermal atmosphere. And we can evaluate the Jeans escape equation at the exobase, and assume that the gas is in complete thermal equilibrium. All right, and so that Jeans escape equation, it depends on this Jeans parameter. So the Jeans parameter sort of gives you an idea of how escape is occurring. It's the ratio of the gravitational energy to the thermal energy. So based on the gravitational energy at the exobase and the thermal energy at the exobase altitude. So for Jeans parameters greater than 3, you can think of it as evaporative type of process. So molecules at the tail end of the Maxwell-Boltzmann distribution, a small fraction of those ones, as they have collisions, they can promote molecules at the exobase to have a speed greater than the escape speed, and that would contribute to the loss of the atmosphere. However, as the James parameter, if the James parameter is really small, corresponding to high temperatures in the upper atmosphere or high atmospheric temperatures, you can really have an outflow type of process. And right, those outflow processes can render that isothermal assumption as incorrect. And right, you can have an hydrodynamic type of outflow or bulk outflow of the atmosphere. And so at higher temperatures is, that genes approximation can really break down and become not applicable. This plot here is showing, I'm sorry, not plot, but this table here is just showing different estimates based on the CO surface densities that we use, similar to the Mars surface density, for different temperatures. If you use the hydrostatic law, where the exobase would occur. So in that first column, you can see as temperatures increase, right, the exobase distance becomes further and further from the surface. And then we show estimates of the gene's escape rate. So because it varies exponentially with that gene's parameter value, you can see that, right, for small changes in temperature, you can have significant difference in escape rate from low temperature to high temperature. And also what's shown in the third column is the estimated genes rate at the surface. And it's just showing how it differs when you estimate escape at the surface compared to escape at the atmosphere, whereas at the exobase, where it's most probable at. So once you get to temperatures at about 400 K, what you'll find is that for these particular surface densities, that you don't obtain an exobase altitude when you use that isothermal hydrostatic law. And that's just because, it breaks down at those temperatures because you have other things, other important dynamics occurring, which I'll talk about a little bit more as we go on. And so, the first thing to point out, differently from that initial Von Drake estimate is that, you have to consider thermal escape. It depends on this exobase density, exobase temperature, right, and the mass of the body and the molecular mass of the species that's escaping. And right, that's just reiterating that genes parameter. And so this plot here is showing the genes escape rates for each of the hypothetical atmospheres if you assume different temperatures in the upper atmosphere. So the solid horizontal line labeled NK17 is the loss rate that I talked about earlier, that 10 kilograms per second. And you can see the temperatures that are labeled with each of the lines showing what the loss rate would be for those hypothetical atmospheres at the different temperatures shown here. And you can see once you get to temperatures of about 400 Kelvin, you get something similar to the NK17 loss rate, but mind you, outflow is really important at these higher temperatures. This is a corresponding plot, but showing the atmospheric lifetime for the different hypothetical atmospheres, and it's just pointing out some important comparisons with it. So even though the thermal escape rates that I showed in this previous slide here, you can see that they can vary quite significantly depending upon basically that exobase altitude and exobase density for each of these curves. Because thermal escape is proportional to exobase density, the lifetime doesn't vary as much as you see there. It's still relatively constant, even though because that escape rate is changing with the density. But what I really like to show here is that once you get to upper atmospheric temperatures that are pretty low for, in this case, CO, once you get to something about 250 K, you start to approach, the lifetime of the moon. So thermal escape isn't a valuable loss process for those temperatures. If it couldn't be the dominant loss processes for those temperatures, or you would have some sort of remnant atmosphere left over. Um, and so one of the things that I'm really interested in is how rarefaction affects escape and how it affects. Oh, excuse me, 1 minute. Sorry, I dropped off for the kids for a moment there. But okay,
No
I'm
problem.
in- I'm interested in how rarefaction affects escape, and it can be really important, especially when you have multi-species atmospheres. So one way to characterize rarefaction in an atmosphere is using this Newton number, and it's the ratio of the mean free path to a characteristic scale length in the atmosphere, typically taken to be the scale height. So when you have really small Newton's number, you have a bunch of collisions. The atmosphere is highly collisional. But as you get to larger values, where escape occurs, um, collisions are infrequent and the gas flow can be really non-equilibrium. And so those non-equilibrium effects can be important for the escape rate and temperature of the upper atmosphere. And right, so the exobase, I just want to point out here, as shown at the top of this slide here, is that the exobase is really a rough approximation, right? Is ambiguous when you really start to think about multiple species, right? Because in the upper atmosphere, these species they don't interact as much, and so they're not in equilibrium with one another, and so it's really hard to use that approximation to a minor species. Okay, so in this study, I used a rarefied gas dynamic to look at a rarefied gas dynamic model to look at escape in these upper atmospheres. And it's a particle tracking tool is equivalent to solving the um, Boltzmann transport equation. And it directly simulates molecular interactions like collisions. Escape and temperature, you don't assume like isothermal, but escape and temperature is explicit to the model. And it doesn't assume thermal equilibrium in this upper atmosphere region. The accuracy depends on how well you can resolve flow gradients and how well you can describe these interactions between molecules. And some of the difficulties are when the Newton number gets really low, it can be, when the atmosphere is really, really dense, right? It can be computationally demanding. So sometimes you have to make approximations about, where you start the model or which regime of the atmosphere you apply it to. Here are some examples here, really looking at when is it appropriate or not to use this isothermal hydrostatic law. And so these simulations results are for a multi-component atmosphere, early lunar atmosphere, where you have CO and you have H2 at about 1% or maybe a little bit less than 1% of what CO is. And the gray figures are showing on the left in the density plot, the gray figures are showing the isothermal hydrostatic law for CO and H2. And then it's compared to the actual model result. And so in this plot at 300K, you can see that CO, the isothermal approximation works fairly well for CO. So you could use that to estimate the gene's escape loss rate in that case. However, you can see that H2, it's limited by its diffusion. And so you wouldn't be able to use the hydrostatic law to estimate the H2 escape rate. You have to think about, you have to think about a diffusion limited type of escape rate. And the figure on the right just sort of is showing the temperature, and it's just showing the temperature change with altitude. And you can see for CO, it's nearly isothermal around 300K. It's a small decrease in temperature due to outflow, due to escape. Because as H2 interacts with it, it takes some of its energy with it as it escapes. But you can see the H2 profile really cools significantly because it's so light, outflow is important. And you can even see at this exobase, they're definitely not in thermal equilibrium, being that CO and H2 have different temperatures. So this, this title is wrong here, but this is if the temperature was 400K, the same comparison. So you can see with density, because the temperature is higher and CO is now even escaping efficiently, you can see that even CO departs from that isothermal hydrostatic law at this temperature. So even so at 400 K, it wouldn't be applicable, right? You need some sort of model that accounts for outflow to estimate escape from the top of the atmosphere. And if you look at that temperature profile, you can see it's really cooling. Both species are really cooling. So the exobase temperature, right? You wouldn't be able to use that 400 K temperature at the exobase. You have to really know, what's the effect on, what's the cooling effect on the temperature. I think I'll skip this slide here, but this is showing an even higher temperature. And well, I'll just mention it briefly. So this is an example of even a higher temperature at 550 Kelvin. Comparing the RGD model result to the isothermal law for CO, but H2O in this case. And you can see even at 550 Kelvin. So, right, you can see the species are well mixed, even up to the exobase, but right, you have this significant decrease in temperature from what's assumed to be the lower boundary temperature at 500 Kelvin. And that's just because, outflow is really important. And so that would be really important for considering the lifetime. This plot here it's just showing when adiabatic cooling or cooling due to escape becomes important. So for this plot here is showing the bottom line is showing the Newton number. So basically a change with altitude, how the density is changing with altitude, and the vertical axis is showing the Jeans parameter at the lower boundary. And each of these lines represents a different hydrostatic isothermal density profile. And for the densities assumed for our atmospheres, you can see for different temperatures. So for like 100 Kelvin, this top line here is showing that you could use that Jeans escape approximation at the exobase for an isothermal atmosphere, and you would get a really good, it's a good estimate for atmospheric escape. But as temperature increases, that approach becomes invalid. So for the profiles that intersect this red line, this is when the isothermal approximation breaks down. These are for temperatures when that breaks down, in which cooling is really important. And some of these profiles don't even obtain an exobase. So right, if the exobase is at Newton number equal to 1, so if they cross this bottom axis here before getting to 1, basically you cannot have an exobase using that isothermal hydrostatic approximation. So it gives you an idea of what temperatures that particular approximation would not be very useful. You need some sort of dynamical model to consider cooling due to outflow, and also for when you have minor species, thinking about diffusion limited type of flow. All right, so I'll move on to energy limited escape here. And the idea behind energy limited escape is an approximation that you can obtain from the conservation of energy equation, the hydrodynamic conservation of energy equation. And if you think about the amount of EUV, so the absorption of UV and EUV into the upper atmosphere really controls the temperature, and that temperature will in turn affect escape. And so the energy limited approximation assumes that all of the energy, the solar energy going into the atmosphere directly goes into lifting the gas out of the gravitational well. And that's what that relationship that's written with that top equation. So right, it's a really broad, sort of broad approximation. It doesn't consider how efficient conduction is. It doesn't consider things like horizontal transport or effects of cooling, right? The approximation is that it neglects the energy that goes into actually heating up the gas and expanding the gas, and it just looks at an upper limit as if you dump that much energy in, how much escape do you get out? And so this is commonly applied to like exoplanets or early Earth, early Mars atmospheres to estimate escape. But it's well, it's well known that it's a, it can be a really rough approximation. But we used it here just to, um, for consistency. And so if you think about Mars, right, is relatively optically thick to UV, and you can estimate sort of a column as to where that UV would be absorbed. And using this energy limited approximation, if we can sort of get the radius at where that maximum absorption is occurring at, then we can roughly estimate a heating rate from the solar UV shown by the term Q. And then we can estimate what the energy limited escape rate was. And so for these absorption cross sections listed here, in the corresponding column in these early atmospheres, that column occurs between this radial range of between 1.2 and 2.1 lunar radii. And using an efficiency of about 20%, saying 20% of that heating goes into lifting the gas out of the well, and using a higher solar EUV flux based on the early sun, some estimates for the early sun, you get a really large energy limited escape rate. And yeah, so, what does that mean? I don't know. I think that, right, it's really a rough upper limit. And its application is still, under scrutiny between different communities. And right, if we think about, sometimes I think it can be a little bit dangerous to use it, because if you think about current Mars, right, if the early lunar atmospheres are similar to what's currently on Mars, current Mars atmosphere isn't undergoing this energy limited escape. And also, we thought about energy limited escape for other bodies like Pluto before, but since then we've seen that it didn't. It wasn't a very good approximation for that as well. So, but for completeness, I wanted to show it. But moving on to non-thermal escape. So also using Mars as an analog, a CO2, CO atmosphere, photodissociation is an important loss process in which UV can dissociate the CO or the CO2, and it can result into high energy oxygen atoms and high energy carbon atoms directly escaping. And this is known to be important at Mars for producing like the hot oxygen corona. And also atmospheric sputtering is important at Mars, in which solar wind and pickup ions can directly impact the upper atmosphere, and they can directly, through momentum transfer, knock an atom or molecule out of the gravitational well, leading to escape, or it can initiate sort of a cascade of collisions like billiard balls colliding, which could eventually eject atoms or molecules. And these two processes have been thought about a lot for current Mars atmosphere. And so we looked at them for the early lunar atmospheres. All right, just checking my time here. Okay. And this plot here is just showing the dissociate. So we can calculate using an early solar flux for the relevant UV wavelength range where dissociation occurs between about 90 and 110 nanometers. We can do a simple estimate to estimate the dissociation rate of CO. And then based upon the dissociation rate at the exobase, we can assume, we can estimate how much of that is lost to escape. And if you do that calculation, was talked about a little bit more in detail in the paper, you get sort of for a broad estimate, I think for the highest surface density used, you get like this large mass loss rate of about 200 kilograms per second. Again, using the early EUV flux, enhanced EUV flux. And we also looked at sputtering. And so we used, sputter theory is pretty common, and there are analytical approximations to estimate, how much yield you get from an incident ion. So we applied that. It's based on, again, solving the Boltzmann transport equations. And so we did that. We used those analytical equations, thinking about protons and helium from the early solar wind, and how they would depart energy and eject CO from these early lunar atmospheres. And we used some previous work, excuse me, based on the amount of flux that could reach the lunar surface in his previous work by Garrick Bethel in 2019. We used that integrated flux to estimate how many protons and helium ions would be impacting the atmosphere. And from that, based on the stopping power of protons and helium within a CO atmosphere, and momentum cross sections between atmospheric neutrals, we could estimate the amount of sputter particles. And we did that for a range here. So depending upon the magnetic field strength, you could have from the paper, you could have between 9 and 33% of the solar wind flux reaching the surface. And so we used that, and we estimated that, and because the solar wind flux could be, up to 100 times larger than the current solar wind flux, we get this broad range of mass loss rates due to sputtering of CO between 6 and 800 kilograms per second. And I'm finishing up soon here. So based on those different processes, we looked at energy limited escape, we looked at thermal escape, and we looked at non-thermal processes, photochemical escape and sputtering. And so this plot here is showing for each of those hypothetical atmospheres what the loss rates would be compared to the assumed loss rate in NK17. So the energy limited escape is really a rough upper bound for thermal escape. And you can see it right, those has the highest rates up here. And you can see we looked at the case of sputtering when there wasn't, when the solar wind had complete access to the atmosphere, and also when part of the solar wind was blocked, due to a possible early lunar magnetic field. And we sort of show a bounding range for that, shown by the circles and the triangles shown here. And you can see that photochemical escape is comparable to that the sputtering loss estimates. And also we show at the bottom is thermal escape for an atmosphere of about 300 Kelvin. So you can see, depending upon that upper atmospheric temperature, which depends upon how much solar UV, EUV is absorbed, non-thermal escape could also be important to consider as far as the loss of these early atmospheres. And and I think we sort of realized that because Mars is sort of a good analog for that. This is the corresponding lifetime. This is the corresponding lifetime for those loss rates. Again, for energy limited, the lifetime is really short, maybe less than hundreds of years. For a non-thermal escape, is comparable to the lifetime in NK17. So lifetimes of like, between say 10 and 100 million years. As you get to 300K, if you just consider thermal escape, right, the lifetime begins to really become large for these hypothetical atmospheres. If the upper atmosphere temperature is 200K, you can see it approaches the lifetime of the moon. And so thermal escape wouldn't be a viable process in this case. And this is just my summary slide here that I briefly wrap up. So the, you know, we looked at relevant loss processes to early moon atmosphere. That would be thermal escape. That would be diffusion limited escape of a minor species. Um, that would be photochemical loss. That would be sputtering. For thermal escape, we really wanted to highlight that it really depends on the temperature at the exobase, the temperature and density at the exobase. Um, so thermal escape depends on the extent of EUV, UV heating of the upper atmosphere. If it's less than 250 K, the CO would stick around too long. If it's greater than 400 K, thermal escape dominates all loss processes. So it dominates those non-thermal loss processes. Uh, Thermal escape of H2, what we found is that thermal escape of things like H2 and H2O, they would occur at rates similar to the diffusion limited rates for those species based on the mixing fraction that's assumed for those that are in the atmosphere. For H2, we found that the lifetime would be really short because it has a large outflow rate. And based on that, you can estimate if you assume that H2 is the dominant source of hydrogen to the PSRs, which probably isn't the case, but if you assume that, you can estimate sort of the type of accumulation rate that it would take, right, to supply those areas based on the lifetime of escape against escape. And let's see here. I will just finish with some sort of caveats, right? I just point out that we assumed the atmospheric masses that were Mars-like in this study to look at the relevant processes, but the link between outgas volatiles and the actual derived surface pressure, that's not well constrained. And that's something that should definitely be worked on in the future. And that's one of the things that Parvati and I have talked about in the past before. These rarefied gas dynamic models play an important role, right? So if you think about these volcanic sources outgassing into a vacuum and how it builds up into a collisional atmosphere, you really need these RGD models to see how that occurs. And we actually have some really good analogs, right? Another important thing that I didn't sort of talk about is that here I assume an atmospheric mass and then I calculate the relevant loss processes. But really, what you have to do is consider the balance between the source and the loss, right? And how that accumulates in the atmosphere. And the Galilean moons are really good studies to do this, right? Io is a current example of how we can think about how volcanism is contributing to a current atmosphere. Also, Callisto, that often isn't thought about, but Callisto has this rarefied atmosphere, and as it passes through, it's controlled possibly by sublimation and by precipitation from Jupiter's magnetosphere. So as it goes behind Jupiter into shadow, the atmosphere can condense. And so you can really have this transient atmosphere going from collisional to collisionless state. And you can use potential observations of Callisto and Io to constrain these early lunar atmosphere models to think about how an atmosphere would evolve from the initial stages of volcanism to the surface pressure that you would get. And once that's done, then you can apply really detailed photochemical models to really constrain what's the upper atmosphere temperature. And that's what's really needed to constrain as far as the thermal escape rate. And thank you for your time.
All right, awesome. Thanks, OJ. That was great. And Andrew is clapping for you via Zoom. He has and both Andrews are clapping for you. All right. So what questions do folks have? All right, I can get us started while other people are thinking of questions. So, OJ, when you have the loss rate as a function of age on some of your graphs, that variation in the loss rate with age is basically related to right, yeah. So, or if you go back one slide, right. So the variation with age is basically due to the variation in atmospheric mass, right?
Yes,
That's what's controlling the shape of the things.
Yeah.
So for instance, so some of Jim Head et al.'s recent work suggests that maybe these atmospheres would have had a much lower mass than some of the masses that Needham and Kring predict. So in that case, so if you wanted to find the loss rate for a much lower mass atmosphere, you could basically just look at a time when the mass was lower and pull out that loss rate, right?
Yeah, you could if the mass for that particular time is comparable, yes, you could do that.
Okay.
Mm-hmm. Yeah.
What other questions do people have?
Yeah, I guess this is Jim Head. I guess that's I guess part of the problem is Parvati brings up that it's not clear given the estimates of the flux from individual eruptions and the discharge of volatiles as a function of time in a single eruption and its duration, whether you actually even in the repose time between eruptions, they're all so low that it's not clear from our GRL paper that you actually can build up much of an atmosphere. So I guess that's a starting point to try, to use that and then think through, as you were saying, Parvati, to see what the implications are there. Does that make sense?
Yeah, I completely agree. That's what I was hinting at in the beginning, is that we really need to start from the assumed outgassing source rate and then see how the atmosphere builds up, because that's really important as far as UV absorption and also the interaction with any solar plasma.
Cool. Okay.
Yeah, this is Tim live and good. I wanted to
Hey,
just,
Tim,
oh,
you
yes,
sound a little bit like a robot.
just a second then.
Oh, I think we lost him.
Yeah.
Yeah.
Wait, now we don't hear you at all.
Okay, now you should be able to hear me.
Okay, yeah, now we hear you really well.
We've just gone to the regular microphone, and to heck with headphones. So there's some complications from atmospheric chemistry and atmospheric processes that you're going to want to keep in mind. You were talking about 300 Kelvin temperature, which presumably is for the thermosphere. It does get colder than that, though, down in the a little deeper in the middle mesosphere, where we have measured temperatures on Mars that have gotten down as low as 90 Kelvin. And a fairly typical measurement, though, would be around between 120 to 200 Kelvin. And for Venus, using the translational broadening of the non-LTE line in the upper atmosphere, we've gotten temperatures that are in the 200 to 300 Kelvin range. So bracketing, of course, the region that the moon is found in today. So temperatures below 300 Kelvin are not unreasonable to consider for the moon. You can't just extrapolate from Mars. We've got Venus on the other side, is still awfully cold in its upper atmosphere. And of course, the reason is that it's a radiatively active molecule, unlike Earth's upper atmosphere. Also, you can't just let CO2 turn into CO over time, because clearly Mars hasn't. And that's my dog. And that's because it's got its vanishingly small quantity of water that interacts with the CO2 to recycle the CO back into CO2. So chemistry can be a significantly complicating factor. And just using the example of Mars, it can complicate it to the tune of billions of years of extended survival. So, that you're going to have to include photochemistry and radiative physics in your atmosphere as well in order to get a structure to look at what happens to it.
Yeah, I mean, I agree with that completely. This is really like a sort of a broad overview. So we looked at a range of temperatures as low as like 100 Kelvin up to like 600 up to like about 600 Kelvin, because we don't know what the upper atmosphere temperature would be. And yeah, I also agree as far as the CO converting to CO2. In this case, right, if it converts to CO2 and it has these low temperatures, right, then that definitely wouldn't work out as far as thermal escape being an important loss mechanism, because CO2 would be around for even longer. So this is really like sort of like a broad bound of escape, like when these different processes are important. I think before we can do the photochemical models, we really have to get a good handle on how the source turns into an actual atmosphere. And then once we get an idea of how the source turns into an actual atmosphere, because right, this volcanic outgassing is probably happening at temperatures of 600 Kelvin plus, right? It's not at the surface temperature. So how much of that initial atmosphere is retained? And then once that's built up, what are the implications as far as UV absorption and solar heating?
Yeah.
Yeah. All right, we have time for one last question, if anyone has one. All right, I'm gonna ask one last question if no one else has one. I'll wait 5 seconds. Okay, I'm gonna ask a question. So, OJ, another thing is, in terms of atmospheric temperature, does it matter, or how much does it matter if you have very different day side and night side temperatures? Like, does it matter that the atmosphere might sort of be cooler and more compact on the night side, and for half the time?
Yeah, that would be really important. So, right, the temperature, it really depends on how collisional the atmosphere is, right? So if it's really highly collisional, in the upper atmosphere, you might think that, that heat is sort of transported, it's transported from the warm side to the cold side, and it could result in a relatively, uniform upper atmosphere temperature. It just depends. I mean, it really depends on rotation and, it would depend on rotation rate and how collisional the upper atmosphere is. But right, if the temperature on the day side and night side are very different, temperature is a controlling factor as far as thermal escape. And so, thermal escape could proceed very differently on the night side and day side if the temperatures are really different, as we sort of discussed using that Jeans escape equation. Another thing that, let's not forget, even if at the moon, let's say that the upper atmosphere temperatures were really cold, such that thermal escape wasn't important, let's not forget that non-thermal escape sputtering can still also be a really important loss processing. And shown here, right, for the early solar wind flux, you could remove these atmospheres on the order of like 1 million years or so.
Right. Yeah. Good point. All right. So we are just over the hour. So unless anyone has any further questions, or I think people are still taking a while to digest this, because you're one of the few people who sort of looked at atmospheric escape in the lunar context, OJ. So people think of more questions afterwards. I will encourage them to reach out to you via email. But this was a great presentation. This is really good, important work. And I think we're 2 minutes past the hour, so we will call it a meeting for today. And so thanks, OJ, again for a great presentation. Lots of compliments coming in the chat.
Thanks, OJ.
And thanks everyone for dialing in. We will meet again in about a month from now.
Thank you.
All right, thank you. Take care.
Yeah, bye, folks. Take care.
Bye, everybody.